Hello, I am Edward Berman, and today I'm going to be talking to you about binomial random variables. I'm going to contextualize them, give some definitions, interpret them, give an example as to where they're useful, and also make some connections. Um, so first, in the greater context, a binomial random variable is an example of discrete random variable, which is a function whose domain is a sample space S, and whose values form a finite or countably infinite set of real numbers. It's called a discrete random variable. We denote them with capital letters X or Y usually. So a binomial random variable is a random variable whose domain is a set containing integers between 0 and n inclusive. So think 0, 1, 2, all the way up to n. And additionally, we say that X follows a binomial distribution NP if P of X equals K is equal to n choose K times P to the K times 1 minus P to the n minus K. And again, it's read X follows a binomial distribution or a binomial variable NP. I would also like to propose an alternate definition. We're going to consider what's called an indicator variable, which takes on the value 1 with probability P, uh, and 0 with probability 1 minus P. So if xi is an indicator variable and y is the sum of indicator variables, then y follows a binomial distribution NP. Well, the alternative definition requires the use of another random variable to define, and so it doesn't stand as well on its own. I think it is important because it gives us a better feel for what a binomial random variable is. It is the sum of uh, events or sum of random variables of the same mean, dictated by the same rule, so to speak, informally. As an example, this example will underscore both why binomial random variables are useful and why it is useful to think about them as a sum of indicator variables. This is the umbrella problem. And people tend to party. They all grab their umbrella. On average, how many people will leave the umbrella they came with? But it's a II is an indicator variable. It takes one with probability P being the probability that the I person gets their umbrella and 0 otherwise. So if we want to consider all of the people, then we consider the sum of the indicator variables for each I person. And to get the mean, we take its expected value, take advantage of the linearity of expectation. Note that 1 times the probability that the I person grabs their umbrella is 1 times 1 over n, which is just 1 over n. So using sum properties, this is 1. I would also like to connect the binomial random variable to other random variables in distributions. First off, a Poisson distribution. X follows a Poisson distribution lambda if the probability of x equals k is equal to e to the negative lambda times length to k over k factorial. And what I'm claiming to you is that this distribution is the limit of a binomial distribution as n goes to infinity and p goes to 0. Uh, I'm not going to go through all the proof, but the trick is to define this lambda, which is equal to np. So we substitute this value in for p. We do some algebra by distributing the n's into the factorial that comes out from this choose, and then we take advantage of the limits as n goes to infinity. So if we solve this rule, these all go to 1. This goes to e to the negative lambda. This goes to 1, and so we get the desired result. For our relation lambda, n tending to infinity is the same as p tending to 0, which is why I only need to consider the limiting behavior of one of these in the proof. And this is useful because it allows us to answer questions about things where we have lots of data points, lots of samples rather, but each of them have a very small probability of happening. For example, a computer screen with a huge number of pixels, each with an extremely small probability of being effective. A binomial random variable is also related to a normal distribution by the central limit theorem, which states that if we have an infinite sequence of random variables with mean mu, such as an indicator variable, invariance sigma squared, where these quantities are finite, then our binomial random variable will actually converge to a Gaussian or a normal random variable in this way. In other words, if we take a binomial random variable, subtract its mean and divide by its standard deviation, and we do this for a large number of trials n, then our binomial distribution converges to a normal 0, 1 distribution. Thank you.